So the goal today is yeah, you want to handle it? Thank you. So the goal today is to prove Riemann-Roch. For a compact surface X, a Riemann surface X, a compact Riemann surface X, but assuming two things, assuming okay, first of all, that there exists a non-constant meromorphic function on X. There exists a non-constant meromorphic function X. That's one technical condition. And second is that dimension of a space of holomorphic one-forms is the genus. Dimension over C of omega X is equal to G equal to genus of X. And this notation that I didn't use very often, but I can just maybe say omega of X is the space of, it's a vector space over C, obviously, space of holomorphic one-forms on X. Okay, so we are going to assume both of these things to be true. The fact of the matter is that both are actually true in general for any compact Riemann surface. They're true. But for general compact Riemann surfaces, the proof is very analytic and needs some time to develop. So instead, I will just assume them. I will prove the Riemann-Roch, and then I will comment on how to prove these things for compact Riemann surfaces in general. By the way, if your surface to start with is algebraic, both of them are much easier to prove for algebraic Riemann surfaces that are given, say, by a homogeneous equation or as a smooth compactification of a smooth plane curves, such things. That's much easier to prove these two things. So that's why it's not unreasonable to assume that. So what I'm saying is that many Riemann surfaces that you see in nature actually satisfy these two conditions for free, more or less. So you don't have to worry too much about them. But now the point is to understand the argument, assuming these two things, because the argument still is quite tricky and intricate. The chain of results one after the other, which is quite interesting to see what's going on. So now Riemann-Roch itself, of course, it just says that dimension of L of D minus dimension of L of K minus D is equal to degree of D minus G plus 1. So this is for any divisor D on X. I mean, this K minus K is a principal divisor, any principal divisor. You know the definition of all of them. And L of D is the set of all meromorphic functions on X, as you remember, which is divisor of F, such that divisor of F plus D is non-negative, right? So this was the definition of this space L. You remember we proved that this is finite dimensional by a kind of induction argument, step by step. We proved in last lecture that this is actually finite dimensional. This is highly non-obvious. To prove that this is finite dimensional, we had to use only one. Two is not used yet, but for the proof of Riemann-Roch, we'll use both 1 and 2. So this is a statement. Okay. So now let's see how we can approach. So there is one main theorem which I want to prove, which is the following. Okay, so I guess the easiest is I just erase now everything that you have, so I just erase them. Have these two conditions in mind because they are used again and again during the proof. So the main result that we will prove is an inequality which is in this proposition. Let K be a canonical divisor. And D an effective divisor.
Effective divisor.
I will define it now, yeah. An effective divisor. So effective means D of P is bigger than or equal to 0 for all points in X. So the index of every point is non-negative at all points.
Because then the degree of D would be infinite.
Pardon me?
The degree of D wouldn't be finite anymore.
No, it is finite because the definition of divisor is that it has compact, it has actually finite.
Zero, sorry. Okay.
Yeah, this is non-zero, yeah.
Okay.
Right. Okay, so so we are working with effective divisors. Then dimension of L of D minus dimension of L of K minus D is less than or equal to degree of D minus dimension of L of K plus 1. By the way, that dimension of L of K is D. If you assume the second statement that I told you, this is what it is. But it doesn't matter for now. So this is the statement. So how the proof goes. So let us write D equal to sum NP times P. P belongs to pi, where NP is positive. So obviously we don't care about the points where this D is 0. Almost all points D is 0. So the set of points where D is not 0, the support of D, we call it pi, and just we write D as such a sum, right? So then let's define some vector spaces now. Let V be equal to direct sum VP, P belonging to pi again, where VP is the set of principal parts of Laurent expansions at point P. So I just write it like this, sigma j from 1 to NP. So CPJ, these are complex numbers divided by z to the power of j, where CPJ belongs to C. Okay? So this is basically the non-trivial part or the pole part of the Laurent expansion at those points, but just from 1 to NP. Obviously, dimension of VP over C, of course, is NP, and dimension of V is obviously some of these dimensions, right?
So what C sub Pj?
For me,
What CPJ?
what's that?
What is CPJ?
Oh, these are complex numbers.
Right.
We just take complex numbers and we form this vector space. These are vector spaces of power series of this form.
So for J going from 1 through NP, for
That's
each
right.
J,
Yes.
you're taking a random complex number.
Yeah.
And what's Z?
Z is the variable.
I'm confused.
So it's like this. You define polynomials, right? What is a polynomial? It's just C of Z, right?
Okay.
You just write A1 plus A2Z plus A2. So this is Z.
Mhm.
And this case is like a Laurent, it's just a negative power.
Okay.
So they turn out to be actually the expansions of meromorphic functions at that point P, at pole at the pole P. Is that clear?
Mhm.
Any questions about this VP? I mean, this is just completely a formal thing I'm just introducing. It's just high school thing now. It's really nothing more than high school right now. But now I put it into good use, comes graduate immediately. Okay, so this is this one, and dimension of V is this one is just sum of NPs, which is degree of V. Right? This D is, of course, when you write it like this is the degree, sum of the coefficients, right? So now define a bilinear pairing. So this is where the interesting thing starts. Define a pairing from L of K, right? Cross V to C. As follows. Okay, so the first thing you have to do, you have to pick a meromorphic one form whose divisor is K, right? Pick a meromorphic one form. Omega such that divisor of omega is K.
How do you know that such a one form exists?
Well, this is actually definition. We said that these canonical one forms are canonical divisors are exactly divisors of meromorphic one forms.
Okay.
So this is for any canonical divisor, there is a meromorphic one form whose divisor is K. So this is, and it doesn't matter which omega we pick. That's the construction. I mean, I'll just pick one and then I will argue with that, and then that's going to be enough for me. Okay, so this is first step. Pick a meromorphic one form such that, and then define, and then for any H here belonging to L of K, and for any V belonging to V. So I just define this pairing now in the following way. It's a residue pairing. We just take residue and add. Okay, so we just define this one, which is I just define H, the pairing of H and V is going to be sum E belonging to pi residue of H omega, okay, times this function, sum Cpj over Zj j from 1 to np at 0. Okay. So now I have to tell you what does this mean, because the way it's written is actually meaningless. The way that I have written it doesn't have a meaning. But now I just give it a meaning in the following way. So why is it meaningless? Because this thing is just a formal object that exists on the level of algebra. This is just a polynomial with negative powers. So now this is a meromorphic one form upstairs on the Riemann surface. I multiply them. Well, this is not clear. You can multiply, actually. You cannot multiply. And then supposedly this is a one form, meromorphic one form, and I'm taking its residue at point z, so at point 0. So everything here is has to be defined. So more precisely, that's what we mean. So we just pick holomorphic coordinates around each p, pick holomorphic charts around each p belonging to pi. So we just choose p belonging to this up, and then there is map phi p into c. So this holomorphic chart phi p is such that sends p to 0. I can do that. P of p is equal to 0. We can pick always a chart that sends the point into 0. So then using these phi p's, I will write this as a form on C. Then write H omega as a local meromorphic one form around near 0. Okay, so once you do that, I don't want to write the formula because it's just a pullback with respect to phi p inverse of that form. You bring it downstairs, right? So you just do that, and you just multiply these two things. This is a power series. This is a power series. Well, it's a finite power series. This is going to be a power series with some finite negative terms, and perhaps infinite number of positive terms. You multiply, you take the residue. Okay?
You repeat that.
What's that?
You repeat that.
Hmm?
You repeat that.
Repeating from where?
So you take H omega as a little.
That's right. So basically, you're okay up to this point, right?
Yeah.
Pick coordinates and then write this H omega as a meromorphic one forms near 0 in C using this holomorphic chart.
Okay.
Because then you can go back and forth between around 0 and around P. Objects around P gets transferred to objects near 0 and vice versa using this holomorphic principles. Okay. Okay. So this is called residue pairing. It's really the main vehicle to prove Riemann-Roch for us. So this is called residue pairing, and this is what it is. So okay, now. So what do you want to do now with this? Okay. So the next step is, let's define some subspaces. Let W subspace of B be equal to subspace of tuples that are principal parts of meromorphic functions in L of D. Okay, so you see, if you have a meromorphic function, whatever, doesn't matter to be in L of D or not. If you have a meromorphic function f belonging to M, right? You can always expand this meromorphic function around those points P. They may be a pole or not, and then you just take the negative, strictly negative part. So principal part. So the only thing is a concept that I define. Principal part of, if you have something like sum an zn, and from minus say m to infinity is equal to sum a minus m oh no an zn, and from minus m to minus 1. This is the principal part of any Laurent series by definition. This is the principal part, right? By definition. So these principal parts obviously have to be here. They are. So note that f belonging to LD means that the divisor of f plus d bigger than or equal to 0. This is if and only if divisor of f at each p plus dp is bigger than or equal to 0. I mean, this implies that the pole part of, or I would say the principal part of.
Sorry, what's the divisor of f at p?
Sorry?
The divisor of f at p, isn't it just the divisor of f?
No, you see, divisor of f is here, but this means this equality means at all points p this has to be non-zero, right? That's the definition of being non-zero divisor. I mean, a positive or non-negative divisor.
Some points and positive at other points.
What's that?
It can be negative at some points.
No. This is the definition of LD.
Okay.
This is the definition of L of D. What is L of D? L of D, this is the second time I'm defining this. I mean, at the beginning of lecture, I also define L of D. L of D is the set of all f such that divisor of f plus d is non-negative. That's
so
the
let's
definition.
say d is equal to p1 minus p2.
Sorry?
Let's say that d is equal to p1.
No, it cannot be negative. D is an effective divisor.
Oh.
Yes, that's the thing.
Oh.
Okay, good point. Yeah. D is a non-negative divisor, it's effective. So D is.
Okay.
Any other questions? And you have to see that from this condition, you see this divisor of fp bigger than or equal to minus np, you see, because this is np, right? I mean, this implies that the principal part of f at p has at most degree, how to say, has a pole of at most in p degree. Okay, the sentence is a bit grammatically maybe problematic, but you see, when you write it, when you write the power series expansion of f at that point, you don't go below np's in negative powers, because this divisor means that the order of f at p is controlled by np. That's what it is. So that's the control, right? Okay, now. So now what we want to, so this is the principal part of that. Okay, so what I want to show is the following claim now. Okay, so the claim is the following. So this claim is inside the proof. Okay, so we will have a proof inside proof inside. So the claim is that dimension of W is equal to dimension of LD minus 1. Okay, let me give you the proof of this theorem, of this claim. Let us give the proof of the claim. So let us define a map, linear map. Define a linear map. So we just define a linear map from LD, yes, to W that sends F to its principal components or principal parts of F. I mean, obviously this map is surjective because I just defined W to be those components here in this direct sum VP, right? That actually are obtained from some meromorphic function F, right? So this has to be surjective. There's no problem with surjectivity. Now the question is, what is the kernel of this map, right? So if you look at it, if you want to understand the kernel, so it's like, so let me call this map, I don't know, maybe alpha, just it's a bad notation, maybe I call it, yeah, alpha, because I want to use. The kernel of alpha is what? So kernel of alpha is the set of all F in LD that all principal parts are 0, right? So this means that the set of all F belonging to LD such that all principal parts vanish.
Isn't that just the set of holomorphic functions?
Sorry?
Isn't that the set of all holomorphic functions?
Exactly. And what is the dimension of that space?
The genus.
No, holomorphic functions.
Oh, one.
One, yes, exactly. That's, you see, exactly as you said, I mean, because all principal parts vanish and there's no other pole anywhere else because it's in LD anyhow. Things in LD don't have poles anywhere else except in this set pi, support of D. So it has to be constant because it's a holomorphic function, and we know that there exists only one holomorphic function which is constant. Okay, so kernel of alpha is one dimensional, and then the result follows. Okay. What did I want to prove? This one. So let me finish here. Implies that dimension of kernel of alpha is equal to 1. This implies the claim. Okay. So the claim inside the proof is proved now. Now we want to say that okay, so I just pick that residue pairing up there just as a point of reference. Now, the pairing between H and V is equal to 0 for all H belonging to L of K and V belonging to W. Can you tell me why this is the case by any chance? If V, the second thing, is in W, and H is anything in L of K, we want to say that the pairing is 0.
Because V doesn't have any principal part.
No, V can have many principal parts, but is in W. What does it mean? It means that it's coming from a meromorphic function on the whole X. So it's the principal parts of the meromorphic functions on X. So this is a global object now, V, and H is also a global object. So this result is a consequence of what was the result about residues we proved? Sum of residues of any meromorphic one form is equal to 0, right? So this follows from residue theorem. So this is for any omega belonging to M1 of X. So this is space of meromorphic one forms on X. Meromorphic one forms on X. Some residues of omega at various points P in X is always equal to 0. Okay. Now, this guy is obviously going to be the residue of a meromorphic one form because these guys come from a function, global object. These are meromorphic one forms already. You multiply, you get a meromorphic one form on the Riemann surface. So the sum of residues is 0. So this is 0. Okay. So if you are on W, then this is 0. Good. Now, we are doing something tricky, a little more even. So pick a basis. Actually, I don't need a basis. No, I don't need this. This was my first attempt. So now see this pairing. Okay, so instead of consider the pairing. So this is a pairing, right? Which is from L of K cross B to C as a linear map. There's some interesting linear algebra going on now, so I'll show you as a linear map. T from V to L of K star. You see, there you can use duality, right? I mean, if you have a bilinear pairing between two vector spaces, you can interpret it as saying at the same time as defining a map, linear map from V to dual of this one. So what is this map? It just sends V to this inner product. I mean, to this pairing of. I mean, this is a function on L of K, linear functional on L of K, which is this one. So this is simple duality going on, but it's good because it gives us some control because it's easier to work with linear maps compared to bilinear functions. So now so the claim is that dimension of kernel of T star. This is the dimension of kernel of T star. Okay, so wait, before going there, let me just. So residue theorem, as we did before, so as we saw, let me put it this way, the residue theorem implies that T of W is equal to 0. That's exactly when I said the pairing between something from W into that is 0. So this means that the subspace, this big subspace W, is actually in the kernel of T, right? So this obviously implies that dimension of kernel of T, right, is bigger than equal to dimension of W But this, of course, we just observe that this is equal to dimension of L of D minus 1, right? It's just that one. So now take T star. So you have a linear map from V to L of K star. Now look at its dual. So it goes the other way around, right? From L of K star star. But this is just L of K. In the canonical way. Is L of K. There's no confusion. You don't need any basis or any choices. This is really isomorphic in a natural way to L of K. Goes into the dual of this other space, V star. Now, claim is that, so our claim is that the dimension of kernel of T star is actually bigger than equal to, let me erase these things. Okay, is actually bigger than equal to the dimension of L of K minus dimension of V minus dimension of W. So for this, we need a relation between rank and nullity of a map and rank and nullity of the dual map. There's a relationship. So if you have a map, linear map from vector space V to W, for example, then you dualize, then there's a relation between those things, which basically actually boils down to the following thing. If you take an n by n matrix, the row rank of the matrix is the same as column rank of the matrix. This is linear algebra 1600, by the way, but it's done in an interesting way now. And I never understood that theorem anyhow, by the way, which is the proof is very strange. And if you understand it, that's great, because you have this matrix, n by n matrix, you just take linear independent rows, all of a sudden this is the same as number of linear independent columns. Quite strange. This is amazing duality. Anyhow, so this follows. So now, so let me write it how this is done. What is the relation? Right. So proof of claim. Again, this is the second claim or third claim, I don't know. Proof of claim again. In fact, in general, for any dual map, dimension of kernel of T star is bigger than equal to, is actually equal to, sorry, dimension of L of K minus rank of T. I mean, this is just basic linear algebra. Right? But rank, we know that is the dimension of leaders. Now rank of T, yes. Rank of T is equal to dimension of V. This is rank plus nullity theorem minus dimension of kernel of T. This is rank plus nullity theorem. But this is less than equal to dimension of V minus dimension of W. So finally, you get that finally we get that dimension of L of K minus rank of T which appears over there, is bigger than or equal to dimension of L of K minus dimension of V minus dimension of W. So this is equal to, I'll just write it again. Well, okay, so this is equal to dimension of L of K minus degree of D plus dimension of L of D dimension of L of D minus 1. Okay, so for this, yeah, this is minus and this is plus dimension of W. That was okay. So this is dimension of W that I proved from the first part of the claim. I mean the first claim. Okay, now this is dimension of this. Now, okay, so this is dimension of V. And so this from here to here is obvious. We have everything because this is exactly my claim one was that dimension of W is this. Degree of D is the dimension of V because dimension of V was sum of NPs of those components, and that's what it is, okay? So now, but now if you interpret it, there's a nice interpretation here. So dually, there exists a subspace, and that's what we need. There exists a subspace U inside L of K such that inner product of, pairing of H and V is equal to 0 for all H in U and for all V in V. So this implies that, and of course, dimension of U this is this rank plus nullity theorem again we are using, and dimension of U is bigger than or equal to dimension of L of K. This is what we obtained over there. Minus dimension of minus degree of D plus dimension of L of D minus 1. And if you, okay, so basically, this is so far. It's quite a juggling of, it's not more than linear algebra and basic things like residue theorem and definition of L of D, L of K, and this thing, but it's a ingenious application of basic facts.
Why does that inequality hold?
Sorry?
That inequality, why does it hold?
Oh, this is because dimension of U is bigger than that this dimension, and this is dimension of L of K. This is the one that we derived here.
Sorry, the dimension of U is smaller than the dimension of L.
No. So what it says, this thing, if you dualize, what did we get with the dual map? Where did the dual map go from to from? You remember? The dual map went from L of K to V star. And this U is inside, see, this T star went from L of K to V star. And we found something here which has which called it U. And we found something that's in the kernel of T star.
Yeah, okay,
So,
okay.
yeah, so you have to. Okay, now, the last part of this main proposition or theorem is the following. Now, to finish it, I mean, it's an interpretation of meromorphic one forms in terms of. So let me. Is that okay? I erase this part? Okay. So let me erase now. Again, I keep the whole thing. Okay. Now. If H belongs to U, this we conclude that H omega vanishes up to order at least in P at each P belonging to P. Hence, divisor of this meromorphic, new meromorphic one from H omega is bigger than or equal to T, i.e. divisor of H is bigger than or equal to T minus divisor of omega wait. Divisor bigger than T. No, that's okay. So this is equal to T minus K, i.e. H belongs to L of K minus T. So far, let's see why this is true. You see that? You see, if H belongs to U, it means that the pairing of H and any V is zero. That's the way we define, right? So what does that mean if H belongs to U then? It means that if you multiply this meromorphic one form, yeah, by this function, the residue at all points have to be zero, because this is true for all points, all components Vp for all P. So it means that this guy must have a zero at that point, which has order at least NP in order to kill all these things. Because that's the definition of things. So now if you have a zero of order at P, this you translate it into the language of divisors. Again, this really means H omega OK vanishes up to that, at each P, divisor of H omega bigger than T. That's what it means. Okay. So then you write this divisor, obviously here in order to derive this, you just write it as this is equal to divisor of H. Yes, plus divisor of omega. And you bring it to the other side. From this inequality, you get this inequality, which is the same thing. And so this is by the way K, our definition of K. And so this means H belongs to L of K minus T. Yeah. Okay, cool. So now and you see this is D minus K, this is K minus T, because the way we defined was switching the signs. So now then we are done, because thus we can just write one line, thus dimension of this shows that dimension of L of K minus T is bigger than or equal to dimension of L of K minus degree of D plus dimension of L of D -1.
Professor? When
Yeah.
you have d minus k, shouldn't that be d minus the degree of k?
No, it cannot be degree because again, this is going to be syntactically wrong.
Okay.
You know what I mean? Because you cannot put degree inside here. It should be divisors only. It's just a question of grammar, not meaning given.
Oh.
You know what I mean? So the language of mathematics is such that if you follow the language, it will stop you from making a lot of mistakes, actually. That's the beauty of language of mathematics. That's non-existent in most other in any other language, actually, because it's very well set. You know what I mean? So we cannot put degree here inside. We don't have L of like 5. It has no meaning. If you have a divisor, you must have L.
Okay.
So, but remember, but maybe your question maybe more is about this. Maybe you meant to ask this. You see, L of D was the set of all F belonging to M of X, such that divisor of F plus D is bigger than or equal to 0. So divisor of F bigger than or equal to minus D. So this equation here.
Could you define L of k minus d for us?
Okay, L of k minus d is very easy. So what is L of, just put here for d, k minus d, right? So L of k minus d is the set of all f such that divisor of f plus k minus d is bigger than or equal to 0. When you bring it to the other side, it becomes d minus k.
But over here, k is oh, okay, right.
K is a what kind of divisor is it?
It's a canonical divisor.
Canonical. Exactly.
Oh.
Which means it's a divisor of a meromorphic conform. These are very special types of divisors. Which is really nothing but the holomorphic cotangent bundle of the Riemann surface. It's good to, I mean, okay, I don't know. There is a way to understand it using this language because if it was good for Riemann, it should be good for us as well. So you don't have to necessarily. Okay, so this is the first part. Okay, now we take a break, and then I will prove Riemann-Roch in the special case that where both divisors d and k minus d are effective, and then we'll do a little more tricks, prove it in general. Okay, guys. For now, we should stop then.